What if a small device could help prevent accidents caused by tired or distracted driving? Hi everyone, my name is Edwin, and in this video, I'm going to show you how I built a drowsiness and distraction detector using a Raspberry Pi, a USB camera, and AI models trained with YOLO. This system detects closed eyes, yawning, and phone usage, and when it detects danger, it triggers a loud alert to wake the driver up. I had this idea because my dad works extremely hard and drives a lot. Sometimes he drives long hours, and like many people, he can get tired. I started to worry about what could happen if he ever felt drowsy behind the wheels. So instead of worrying, I decided to build something that can actually help. This system constantly watches the driver using a camera. It uses three main things: closed eyes, yawning, and uses a phone. If any of these are detected for too long, the system plays a loud beep to alert the driver.
I would demonstrate the entire process of how I built it, but before that, let's show the results. Okay, let's get on to the build. I used a Raspberry Pi, a USB camera, and a buzzer for the alerts. The Raspberry Pi is powerful enough to run AI models while still being small and portable, which makes it perfect for this kind of project. On the software side, I used Python for programming, YOLO for object detection, PyCharm as my coding environment, and VNC Viewer to remotely access the Raspberry Pi. I also had help from a teacher, especially during the training part, since training models was something that I was still learning. This script automatically splits my dataset into training, validation, and test sets, which is required before training a YOLO model. First, I import 3 Python libraries. OS helped me work with files and directories. Shuttle used to copy files from one folder to another, and random helps me shuffle the dataset so the split is fair and unbiased. At first, the line sets a random seed. If I enable it, the dataset will be the same every time I run the script. I left it commented out so the data is randomly shuffled each run. This helps prevent bias in training. Now the next function handles the entire dataset split. It takes the image folder path, the label folder path, a new output folder, and the train, validation, and test ratios. Here I read all image files and label file names into 2 lists. Each image should have a matching label file with the same name. Next, YOLO requires images, names, and labels it match exactly. This part removes file extensions like JPG and .txt so I can compare file names correctly. Next is matching images and labels. This line creates a list of correctly matched image label pairs. Only files that exist in both folders are included. This checks for errors in the dataset. If an image doesn't have a label or a label doesn't have an image, it gets detected here. If there are missing labels or images, the script prints them out. This helped me to fix the dataset mistakes before training. This step also saved me from training failures later. Next, this randomly shuffles the dataset so the training data is not ordered. This improves model generalization. Next, the dataset is split into 80% training, 10% validation, 10% testing. This is a common split used in machine learning. Now, this creates a correct YOLO folder structure for the training dataset. The new image directory equals ospath.join new file path, train images. New label directory equals ospath.join new file path. This makes the image and labels must be separated into image and label folders. The next step, we try to copy the training photos. The Shuttle copy old image path, OIS image path join new image directory image file. This basically means the script copies images and labels into the training directory without modifying the originals. The next step is the validation process. The validation set is proceeded the same way as the training set. The validation data helps check model performances during the training. The test sets processing. The test section is used after training to evaluate how well the model performs and unseen data. Next, it proves that all data training is completed. Once everything is done, the script confirms the dataset split is complete. Next is if _name equals name. This ensures the function only runs when the script is executed directly, not when it's imported. The next is defining paths. File path equals data JPEG images, label path equals data labels, new file path equals VOD dev kit. Here I define where my images are, where my labels are, and where the new dataset will be created. The final folder structure is VOD dev kit, train, val, and dataset. Next, running the split. Split data, file path, label path, new file path, train rate 0.0, val rate 0.1, and test rate 0.1. This line runs the entire dataset splitting process. After this, the data is ready for YOLO training. The script helped me properly organize my dataset, which is extremely important for training accurate models for my drowsiness and distraction detector. Merge both scripts into one for a smooth explanation section. Next time, I can rewrite this at a separate level. Now, I'll explain the main training file I use to train my YOLO detection model. This file controls how the model is trained, what data it uses, and how long the training runs. First, importing YOLO. This line imports YOLO class from the Ultralytics library. Ultralytics provides a ready-to-use implementation of YOLO for training, validations, and inference. Next is the main program check. This line ensures what the training code only runs when this file is executed directly. It prevents the training process from starting accidentally if the file is imported from somewhere else. Next is creating the YOLO model. Model equals YOLO 11 and .yaml. Here I create a YOLO model using a configuration file. This file defines the network architecture, like how many layers and parameters this model has. The M version stands for Nano, which is lightweight and suitable for devices like the Raspberry Pi. Smaller models are faster and use less power, which is important for real-time detection. Next is model load. This line loads pre-trained weights into the model. Pre-trained weights allow the model to start with existing knowledge instead of training from scratch. If I comment out this line, the model would train from zero, which usually takes longer and needs more data. Next is results equals model train. This line starts the YOLO training process. Everything inside these parentheses controls how the model learns. Next is data.data.yaml. This tells YOLO where the dataset is. The data.yaml files contain dataset paths, class names, number of classes. Without this file, YOLO wouldn't know what it's training on. Show data.data briefly. Next is epochs equals 100. An epoch means the model sees the entire dataset once. I set it 100 epochs, means the model goes through the dataset 100 times to learn patterns like closed eyes, yawning, and phone usage. Next is batch size. Batch size defines how many images are processed at the same time during training. A batch size of 16 is a balance between training speed and memory usage. Larger batch sizes need more GPU memory. Larger batch sizes needs more GPU memory. After training my YOLO model on my computer, the next step was getting it to run on a Raspberry Pi. This required remote access, model conversion, and optimization for a low-power device. I used VNC Viewer to remotely access the Raspberry Pi's desktop from my computer. This allowed me to see Raspberry Pi's screen, run Python script, and debug problems without connecting to a separate monitor, keyboard, or mouse. VNC Viewer basically lets my laptop control the Raspberry Pi as if I was using it directly. I installed the Raspberry Pi OS, enabled VNC in the system settings. Once connected, I could open up the terminal, run Python, and test the camera in real time. The model that I trained was saved as a .pt file, which is a PyTorch file. The problem is that PyTorch models are heavy and slow on devices like Raspberry Pi. Running .pd models directly would cause lag and low frame rates. Now, NCNN is a high-performance inference framework designed both for mobile and embedded devices. It is much lighter than PyTorch and runs efficiently on ARM processors like the Raspberry Pi. NCNN makes real-time detection possible on low-power hardware. Now, I first exported the YOLO.pd model into an intermediate format. Then, I converted it into the NCNN format, which produces files optimized for fast inference. This step reduces model size and increases speed. This conversion step is necessary for real-time performance on the Raspberry Pi. After conversion, I copied the NCNN model files into Raspberry Pi. These files are placed inside my project directory, so Python can load them easily. Now, the Python script running in VNC Desktop using VNC Viewer, I opened the Python detection script directly in Raspberry Pi. This script loads the NCNN model, reads video frames from the USB camera, and performs detection in real time. The camera continuously captures frames, and the NCNN model checks for closed eyes, yawning, phone usage. Bounding boxes are drawn on the screen so I can see what the model is detecting. Now, when the model detects dangerous behavior, the Raspberry Pi triggers a loud beep. This alert is designed to immediately get the driver's attention and prevent accidents. Now, using VNC Viewer made development easy. Converting the model to NCNN made it fast enough to run on the Raspberry Pi. Together, they allow me to deploy an AI safety system on real hardware. This step transformed my project from just a trained model into a real world that can save and keep drivers safe. Before the AI model can work, we need to understand the hardware. In this section, I'll explain how Raspberry Pi connects to a USB camera and a buzzer, how the GPIO pinout work, and some of the important modules inside the Raspberry Pi. The USB camera connects directly to one of the Raspberry Pi's USB ports. Because it's a USB camera, the Raspberry Pi automatically detects it without extra drivers. That makes USB cameras very easy to use compared to CSI cameras. This command checks if camera is detected. If I see /dev/video0, the camera is ready to use in Python with OpenCV. The buzzer is used to alert the driver when dangerous behavior is detected. One wire connects to the GPIO pin, another connects to a GND, which is ground. Always make sure the voltage matches the buzzer's requirements. Raspberry Pi GPIO pin output 3.3 volts, not 5 volts. Raspberry Pi has 40-pin GPIO header. The GPIO stands for General Purpose Input-Output, meaning these pins can send or receive signals. These pins provide 3.3 or 5 volts power to external components. Ground pins complete the electrical circuit and prevent damage. These pins are programmable and can be used to control LEDs, buzzers, or read sensors. Some pins support protocol like I2C, SPI, UART. Now, GPIO pins work in two states. High means on or 3.3 volts, low means off or 0 volts. By changing a pin from low to high, the Raspberry Pi can turn devices on and off. In Python, I control the buzzer by setting a GPIO pin to high when an alert is triggered. When the danger is gone, I put the pin back to low, turning the buzzer off. This is how the Raspberry Pi physically reacts to AI detections. Now the CPU is the brain of Raspberry Pi. It handles Python code, AI interference, and system operations. RAM is memory. RAM temporarily stores data while programming are running. More RAM allows better performance when processing images. This module handles USB devices like the camera, keyboard, and mouse. The HDMI outputs allows the Raspberry Pi to connect to a monitor for display and debugging. These modules provide internet connectivity, which is useful for updates and remote access using VNC. This controls all input and output pins and allows communication with external electronics. The micro SD card accesses the Raspberry Pi hard drive. It stores the operating system, Python code, and AI models. The Raspberry Pi is small, affordable, and powerful enough to run AI models. It can interact with real hardware using GPIO pins, making it ideal for real-world safety systems like this one.
To conclude, this project started with a simple concern, caring about someone I love. From began as worrying for my dad turned into a real-world engineering project that combines artificial intelligence, programming, and hardware. Along the way, I learned how to prepare and label datasets, train detection models using YOLO, convert models for edge devices, deploy AI on Raspberry Pi, and connect software to real hardware using GPIO pins. The system can detect closed eyes, yawning, and phone usage, and immediately alert the driver with a loud sound. It doesn't replace human responsibility, but it can help prevent dangerous moments caused by fatigue or distraction. This project taught me not just technical skills. It taught me patience, problem solving, and how to turn an idea into something real. I also learned the importance of asking for help, and I'm grateful for my teacher who guided me through the model training process. In the future, I hope to improve this system even more, making it faster, more accurate, and smarter, with features like head pose detection, better night performance, and advanced alerts. At the end of the day, technology is powerful when it's used to protect and help people. This project is my step towards using engineering and AI to make the world a little safer. Thank you for your watching. If you enjoyed this video, please like, subscribe, and feel free to ask questions in the comments. And most importantly, drive safe.